Hi, welcome to another Math for Honors lesson. I'm Kirk Weiler, and today we'll be looking at linear versus exponential functions. I think this is a particularly nice topic at the pre-calculus level because you've formed equations of linear functions and exponential functions in earlier courses like Algebra 1 and Algebra 2. And you've probably even compared and contrasted these two functions. What's remarkable is how similar they are, even though they seem very different from the way their graphs look. You know, that classic straight line, obviously, for linear, and that curving exponential, either increasing or decreasing. So let's get right into it and compare and contrast. And let's take a look at exercise 1 and see what you already know. All right, this is a good litmus test for you. In this exercise, what we have are two functions given in table form for various x values. And what you might want to note, and this is important, is that the change in x is constant. In other words, we are constantly adding 3, right? Our delta x is a positive 3 units whenever we go from one input to the next input. Uh-oh. All right. So that's kind of important. Now, one of these functions is linear, and one of them is exponential. And in letter A, we're asked to figure out which one is linear. So what I'd like you to do is pause the video for a moment, look at the outputs for both the function f and the function g, and see if you can figure out which one's linear, and try to come up with some kind of explanation why. Pause the video now. Alright, hopefully you figured out that function g is the linear function. Now what a lot of students will do, and this is correct, is that they'll take a look at this and they'll go, to go from here to here, my change in y, I'll call it g just to distinguish it, is a positive 6 units. And over this interval, the change in y is also a positive 6 units. Hi, Norton. Right? And each one of these intervals, and it's important, it's got to be equal for all of the intervals. Each one of these intervals, we get a constant increase in y. Now, the reason that that's happening is because we're getting a constant increase in x, right? The idea of a linear function is that the ratio of the change in y to the change in x is always the same, right? That average rate of change. In this case, delta g divided by delta x is always in that ratio of 6 to 3, or 2 units of y, right, for every 1 unit of increase in x. Right? And that's linear. Keep in mind, some of you may have already started to study the derivative, as we have in our course, and that's to contrast that with dg dx, right? That's not your average rate of change, but your instantaneous rate of change. All right, so the key with linear, right, is that you're getting this constant additive process. For any given delta x, in this particular table, delta x was 3, we're always going to get the same delta y. So the same amount added on. So y2 will always be sort of y1 plus the same delta y, a consistent delta y for a consistent delta x. So obviously then, function f has to be the exponential one. But what's true there? What's true there? So pause the video now and see if you can come up with a different pattern. It's clearly not additive. If you go from 16 to 24, that's going to be a change in 8 units. To go from 24 to 36, that's going to be an increase in 12 units. So immediately not linear. But what is the constant change? What gets you from one y value to a y value that occurs 3 units later in terms of x? Pause the video a little bit and think about that. Alright, this is always harder for students to see. But in the case of f, what's true about 2 consecutive y values isn't that their difference is constant, right? Isn't that what this means? Delta g equals 6. It means that y2 minus y1 is always a constant. But in the case of this exponential function, it's the ratio of 2 consecutive y values for a given delta x. So for instance, right, if we take a look at 24 to 16, we find that that ratio is 1.5. Likewise, if we look at another y2 to y1, or maybe y3 to y2, that would be the better way to look at it, we look at 36 to 24, we also get this 3 to 2 ratio, or 1.5, right? Keep in mind what that's really saying is that that next y value can be calculated by multiplying the previous y value, right? And again, this is for a given delta x, right? Delta x equals 3. So in fact, if that pattern holds, right, we could actually predict the what would the next x value in the table be if we kept it, right? 18. And then the next y value for f of 18, so to speak, we could have taken the previous y value, 81, and multiply it by 1.5. Right? That actually doesn't turn out to be all that nice because 81 is an odd number. But the point is, for an exponential function, we're getting a constant multiplying effect, right? Linear, it's a constant additive effect for a given delta x. For exponential, it's a constant multiplying effect. This can be summarized quite nicely in the next sort of box, if you will. I know that we normally think about linear functions as y equals mx plus b. But one way that's kind of nice to rephrase it is to switch sort of the order, put the b first and the mx second. Of course, we all know what the b means, right? That's our y-intercept. All right. When we look at a linear model this way, what's kind of cool about it is we can think about it as saying, hey, look, we're going to start at a y value of b. We're going to start there. Of course, that means by starting, it's x equals 0. And then what happens is that we get to add on m x times, right? Because isn't that really what multiplication means? It means, we're getting m x times. I know that many times we think of it as getting x m times, but in this case we really can think about it as, all right, my slope is m to 1, and I've got x of them, so if I go over 1, x times, then I get to go up by m. Now exponential, on the other hand, your classic exponential, y equals a times b to the x. In this situation, the a is our y-intercept, right? Our value when x is equal to 0. And this time, instead of adding something x times, we're multiplying by something x times, our base. So there's a lot of similarities here. This starting value plus a constant multiplier effect in the case of exponential, or a constant additive effect in the case of linear. So let's see how much you've understood so far. In exercise number 2, we're again given data in a table, and we're asked if the function is linear, exponential, or neither. All right, what I'd like you to do is pause the video, take a look at what we did in the first exercise, think about what was in that box and the discussion, and see if you can figure out which type of a function this is, if either. Pause the video now. All right, hopefully what you figured out was that neither linear nor exponential would fit whatever function we have in this table. So let's kind of analyze. Let's take a look at linear, right? For linear, what we know is that for a given delta x, right, if delta x is given, we should have a consistent delta y. Right, the change in y should be consistent. All right, well, the delta x is quite clearly 2 here. All right, but then if we look at our delta y, our first delta y, which would be 4 minus 8, remember, y2 minus y1, well, that's negative 4. Our next delta y is going to be 2 minus 4, and that's negative 2, and I wouldn't calculate anymore, right? They're not the same. Now, the reason that we don't have to calculate the average rate of change, because technically that's really what we should be doing, the reason that we don't have to calculate delta y to delta x is because delta x is this constant 2. All right, let's try exponential. All right, to test to see if this is exponential, what we need to see is and so it's very, very difficult to write and talk at the same time. That kind of looks like an H. Whoops. Go back to my pen. Exponential. Wonderful. The key with exponential is that the ratios of consecutive y values have to be the same. So let's take a look at y2 to y1. In this case, 4 to 8 would give us a ratio of 1/2. Now remember what that ratio means is it's literally what I'm going to be multiplying this by to get that. Right? In our next case, we'll continue to say y2 to y1 if you want to think about it as y3. I respect that. That would be 2 to 4, and that's also a ratio of 1/2. In other words, again, I can multiply this by 1/2 and get to that. Now, if this is exponential, then when I multiply this by 1/2, I should get to that. But clearly, 2 times 1/2 isn't 0. Just going with the straight ratio test, y2 to y1 would be 0 to 2, and that's a ratio obviously not of 1/2, but of 0. So this is a big, fat neither. All right. So let's keep going. Obviously, one of the things that we want to be able to do with mathematics always is be able to model real-world situations. So in exercise number 3, we're going to be talking about deer in New York. And I got to tell you, if you live in New York or you live in the great Northeast, deer are often on your mind. I've hit more deer with my cars than I ever want to think about. So I like to think about how quickly deer populations are growing. Well, maybe I don't like to think about it, but I do think about it. So these are some realistic numbers. In 1990, it was estimated that there were 3.2 thousand deer in New York State, and in the year 2000, 4.8 thousand. All right, these are kind of interesting units because we're working in thousands of deer. Keep that in mind, thousands of deer, about thousands of deer as we work through the problem. So what we're going to do is we're going to model this deer population with a linear function and with an exponential function, and then we're going to kind of compare and contrast. So let's take a look at letter A. It says determine a formula for the population in thousands of deer as a function of the number of years since 1990, assuming that the growth is linear. So you always want to pay attention to what kind of model we're going in with. All right, we're gonna assume we have a linear model. All right. Now you can go with a lot of different forms of linear. You can go with y equals mx plus b. Right, the slope-intercept. You can go with the point-slope form, a variety of different things. Either way, we're going to need to get some basic definitions down. So since we're talking about modeling in the number of years since 1990, 1990 throughout the problem is going to serve as our t equals 0. It's another thing you always want to pay attention to when you model, especially when you model functions of time, is are we actually using the calendar year as our input, or is there a particular year that serves as t equals 0? That's actually the most common, because who would really want to have to substitute values in like 1990? Sometimes that could be convenient, but here's what we have, right? And so we know that the population at t equals 0 is 3.2 thousand, and the population at 10 is 4.8. So throughout this entire problem, whether we're talking about linear or exponential, keep in mind that what we really have are 2 points that lie on these functions. And I say functions because we're going to do linear in part A and exponential in part B. Okay, now notice we have the output to this function when the input is 0. To me, if you know the y-intercept of a function, then it makes sense to use the slope-intercept form of the line, right? If we didn't, then I might go with point-slope, but I already know the b. What I need to know, though, is the m. Why don't you pause the video for a moment and calculate the slope of this linear function, and also consider what the units are. Pause the video. All right, let's take a look at our calculation for slope. So slope should be easy, right? I mean, you've done slope a million times. We're going to do a little y2 minus y1 divided by x2 minus x1. Work out all the details. Don't feel the need to write it as a fraction. Slopes are nicely written as decimals. Now think about the units here. Did you get those? They're a little bit tricky. They're thousands of deer divided by year. That's a little bit weird, or per year. It's a little bit weird given that it is the decimal. If you thought really hard about that and multiplied that 0.16 by 1,000, what you would find is you'd say, oh, it's 160 deer per year. What's nice about having the units there is it really gives us a nice physical interpretation, right? We've got an increase in deer population of 160 deer per year. Let's write down our final model, though. You could certainly write it down in the standard form. That's probably what most people would write down. P equals 0.16t plus my y-intercept. I sort of like it. Again, I've become more and more of a fan over the years of looking at it this way. You know, the idea of, hey, we're starting at 3.2 1,000 deer in 1990, and then we're getting an increase of 0.16 thousandths of deer per year. So I kind of like this form, but either one's perfectly okay. Now let's come up with an exponential formula in letter B. I'm sure linear formulas are ones that you're more comfortable with, but let's write down the general form of an exponential. So a simple exponential, one that has not been shifted horizontally or vertically, is always going to have this form, a times b to the t. All right. Now again, we've got these 2 points that we're working with, 0, 3.2 and 10, 4.8. We should know about our exponential models that our multiplier here is our y-intercept. So we already have that value, right? We might as well just substitute it in. Y equals 3.2. And now we could put a little dot. Most of the time what people will do is they'll put a little parentheses here to sort of separate. I always find that a little bit weird because parentheses are there to really group something. And yet in this case, they're not really doing anything except for holding the value b and really letting us know that the b is being raised to the t and the 3.2 isn't. All right, so we still have to find the base of this exponential. Pause the video for a second and think how you use that second point to figure out b. Did you think about it? This is a very common theme in math. What we're going to do is we're just going to simply substitute that point into the equation. So we're going to get 4.8 equals 3.2 times b to the 10th. Right? So we're just going to do this every time we're missing a parameter in an equation. Maybe not every time, but very often when we're missing a parameter, a constant in an equation, we solve for that constant by substituting in a point that we know, and hopefully that leaves us the thing left. Now, we have to still solve for b. For some of you, this might be a little bit challenging. You might want to pause the video now and think about how you solve for b. For my students, I always tell them, look, if the variable shows up once, and only once, I don't care how complicated it is, just identify what's been done to the variable in terms of order of operations and then undo it. So for us, b has been raised to the 10th and multiplied by 3.2 in that order. So we're going to undo it by first dividing both sides by 3.2 and then getting rid of that 10th power. I would not simplify this at all. To get rid of a 10th power, we take a 10th root. That is most effectively done on the calculator by thinking about it as a 1/10th power. So we're going to evaluate this purely on our calculator. There's no way to really do that by hand. All right. So what I'd like you to do is take a moment, put that into your calculator, and make sure that you can evaluate it. Be careful. Use good parentheses. Think hard about it and see if you get the same answer I do. All right. Let's do it. So if we enter this into our calculator, and you're very, very careful, on a calculator that doesn't have any kind of real fancy schmancy stuff on it, very often you're going to have to enter it like this. Being very careful with the parentheses, and that's going to give us a b of 1.041 rounded to the nearest thousand. We still should write down our model. P equals 3.2, just enough room for it too, times 1.041 to the t. Try not to use x if the model is phrased in terms of time. There we go. All right, what's nice about having the exponential model now is that we can think about the percent yearly growth rate, and that's letter C. It says, based on your exponential model, what is the yearly growth rate? Pause the video for a moment and think about what, based on that equation that I just poorly circled or potatoed in, what would be the percent yearly growth rate? Are we getting 8.7%? What are we getting? Pause the video. All right, hopefully you came to a very easy conclusion. Hopefully you looked at this and you said, oh, I recognize this form. But if that doesn't look very neat, this is telling me that I'm getting a 4.1% growth rate per year. Right? Now, we can't redevelop this in this lesson, but hopefully you know, oh, if I'm getting a 5% growth rate, right, I would multiply by 1.05. Right, if I was getting a 12% growth rate, I would multiply by 1.12. That's a little bit trickier because we have that extra decimal hanging on. And of course, some students might make the mistake and say that they're getting a 41% growth rate per year, but then we would be multiplying by 1.41. So pretty nice, right? Just by solving this, we can tell the percent growth rate. That's kind of analogous to going up to letter A and knowing that the linear growth rate, the additive growth rate, if you will, is that 0.16 thousandths of deer per year. Here, this really does have, this has units. It's 4.1% per year. All right. Now, letter D says graph both models in a window appropriate to show the population after 50 years. Okay, this could be a little bit tricky, and you're going to do it on your calculator, but you're going to have to think about a Y window and you know, what would appropriately show both models. So why don't you pause the video and take as much time as you need to try to create that graph. Then draw a good sketch of it. Try to draw something that really conveys a proper picture, and then we'll go through it on the graphing calculator. All right, let's take a look. If we open up our graphing calculator, what we're going to do is put our linear model into the first equation. Of course, we have to put it in terms of x. And then I'm going to put in my exponential model, hopefully, or not. Let's try that again. 3.2 times 1.041 to the x. All right. So I've got my two models. I'm using my keyboard to enter these. I hope that's okay for you. And now I want to graph it, and it says for the first 50 years. That's kind of tricky. One thing that I like to do in a situation like this is I like to go into my table. And all I'm trying to use my table for is to sort of see, you know, what my values are doing over the next 50 years. So what I'm going to do is I'm going to set my delta table to be 10, and then I'm going to take a look and see where this linear and exponential function are. So my linear function is up to 11.2 thousand deer, and my exponential is up to 23.9 thousand deer. So obviously the exponential is much larger. If I wanted a convenient value at 50, maybe say 25. All right, so let's go 0 to 50. Yeah, sure, 0. And what did we say, 25? All right, let's take a look at the two graphs. There's my linear, there's my exponential. Now, one thing that's very, very sort of difficult to tell is what's going on in this portion of the graph. I'd like to do a little bit of a zoom on that really quickly. I know I didn't ask you to do that in the problem, but let's take a look and use what's known as our zoom box. All right, what we're going to do is we're going to draw a box around that portion. Excuse me for the amount of time that this takes. Start my box a little bit lower. I just really want to see what is happening in this portion, because it sort of looks, to my eyes, that the exponential clearly outpaces the linear, but does it just immediately. I get the feeling that the picture might be a little bit more impressive than that, but not much. If we looked at this, and I'll magnify it in my own graph over here, here's what we would see. And this, there we go. Bye-bye, calculator. I don't know a good way of keeping them on the screen at the same time, but I'm sure there is one. If we really took a look at both models, they're both starting at 3.2, and then our upper reach is 25. The exponential model grows very, very quickly, to the point where we saw it was at, what, about 23.9 or something after 50 years, 23.9 thousand. The linear kind of does something like this, and I know I'm kind of exaggerating this, but sometimes we do that. We could even speculate on what that crossing point is, but the linear is slightly more than the exponential at the beginning, and then they cross. Regardless, letter E, the question there is still very, very applicable. In the long run, which model grows more quickly, linear or exponential? And there's no question, exponential. In fact, what I emphasize then in the box at the end is that one of the really remarkable properties of an exponential function is, as long as that exponential function is growing, as long as it's growing, and remember, an exponential function, a times b to the x, will grow as long as b, our base, is greater than 1, and we'll just assume a is also positive. right? As long as b is greater than 1, an exponential function grows, and every exponential function will eventually catch up to any linear function no matter how steep. No matter how great the slope is, even for really big slopes, and I'm not claiming that the last one had a really big slope, but for really big slopes even, that exponential, even if it were 1.00002, would eventually catch up. And that's what we're referring to when we say that something grows exponentially. When they see that something is growing very fast, and they say, that's growing exponentially fast, that's what they're really getting at. It's a very, very fast growth rate over time. Anyway, that's our lesson for today. Thank you for joining me as always. Until next time, keep thinking and keep solving problems. Take care.